Welcome to my channel, The Canadian Physics Tutor. This is my first video in a series where I teach you all of grade 11 physics. Today, in this video, I'll begin by teaching you how to read measurements on analog instruments, how to properly record these measurements using significant digits, and how to perform operations with these significant digits. Firstly, let's go over some common types of measuring tools. There are things like rulers, protractors, and graduated cylinders. Now, rulers measure lengths or distances, while protractors measure angles, and graduated cylinders measure the volume of liquids. Now, these three are analog measuring tools, which means that they have a physical scale with markings that you read yourself. This is opposed to digital measuring tools, such as a digital mass balance, which has a digital screen providing a measurement directly. Now, how would you measure the position of this dotted line on ruler A? Don't look at ruler B for the time being. We'll look at that next. Now, we can clearly see that the measurement lies between 3 and 4 centimeters, but we must come forwards with a second estimated digit. So, for now, we could write 3 point something centimeters. Now, this estimated digit is obviously between 3 and 4 centimeters. If we create a marking to split the division in half, then we will find that it is somewhere between 3.5 and 3 centimeters. Now, because this seems as maybe you could say 3.25 centimeters, because we are only going with one estimated digit, and because it could be either 3.2 or 3.3 centimeters, I am going to go with 3.2 centimeters. But what if you chose to go with 3.3 centimeters instead? Would this change anything? Well, it would. But we can account for this by implementing something called absolute uncertainty. And absolute uncertainty essentially tells us how much a measured value could vary because of the limits of our measuring tool and our visual estimation. It is written with a plus minus symbol and is almost always written with one significant digit. So, for example, you could say, I'll just denote this as x for now. And in regards to significant digits, more on what those are later. Now, typically, absolute uncertainty is written as half of the smallest scale division or graduation. But if you have a widely spaced scale, such as what we have here, and also, if you are confident in your visual judgment, then you may estimate up to a fifth or even a tenth of a division. By going with a fifth of this 1 centimeter division, we end up with a reasonable uncertainty value of 0.2 centimeters. Then, this lets us write the measurement cleanly, and let me just erase all of this. This lets us write the measurement cleanly as 3.2 centimeters plus minus 0.2 centimeters. The true value of this measurement then can actually be a little bit higher than 3.2 centimeters, or it can be a little bit lower than 3.2 centimeters within a margin of 0.2 centimeters on both sides. A reading of 3.3 centimeters, therefore, would still fall within this uncertainty range, so the difference is not a major issue. Now, let's take a look back at ruler B, and you can pause this video to give it a shot. First, we know that the position of the marking is 3.2 centimeters something. So for now, I'm just going to write 3.2, I'll just leave this blank for now, centimeters. Or I'll just leave an X there for now. First, we know that the position of the marking is between 3.2 and 3.3 centimeters, but it seems to be a little bit to the left of the middle, which would be 3.25 centimeters. So I will go ahead and write 3.24 centimeters. Now, because this is a relatively small division, I will write an uncertainty value of half of this division, which would be 0.05 centimeters. And so now we have a final measurement of 3.24 centimeters plus minus 0.05 centimeters. Now, it's worth mentioning that for digital instruments, such as the aforementioned mass balance, the uncertainty value is usually provided on the manufacturer's website. In the case where it isn't, then you should use the smallest value that the instrument can display. For example, if you have a digital mass balance that can read to the nearest 0.01 gram, so say you had 65.41 grams. Let me just rewrite that. Then its uncertainty may be written as 0.01 grams. So far, we have seen that measurements are not perfectly exact. They depend on the measuring tool and our estimate. This leads us directly into the idea of significant figures. Significant figures are the digits in a measured value that actually carry meaning. And whether you call it significant figures, sig figs, significant digits, or even sigdigs, they are all the same thing. Every digit that you record in a measurement is deemed as significant, and there are rules determining which digits are significant in measured values. Now, let's look at some rules to determine which digits are significant. Firstly, all non-zero digits are considered significant. So the 1 here, the 9, the 4, and the other 9, they're all significant. Zeros between significant digits are also significant, and you might have also heard them referred to as sandwich zeros. Trailing zeros after a decimal and non-zero digit are significant. So for example, 68.340 and 25.0. Underlined zeros are also significant. For example, this zero that is underlined here, 0.105, all of these digits then would be significant. Trailing zeros with no decimal are insignificant, and so they are not counted in our significant digit rules. So the only two significant digits in 89,000 are the 8 and the 9. However, back to rule number 4, if you chose to underline, say, the last zero, then these other two zeros right here become sandwich zeros, and so all 5 of the digits would then become significant. Additionally, leading zeros to show the decimal point of your value are also insignificant. So in the value 0.0471, only the 4, the 7, and the 1 are significant. What about some exceptions to the rule? Well, mathematical constants and exact countable numbers are rendered as infinitely significant. So things like pi, Euler's number, the golden ratio, or if you were to physically count 5 apples. These values are never considered in significant digit rules, and this is because they possess no measurement uncertainty and will never limit the precision of your final calculated result. Now let's try solving these problems. Determine how many significant digits are in each of the following numbers. We have 0.019. Because these are leading zeros, only to show the positioning of the 1 and the 9 after a decimal point, then only these two numbers here are significant. So this number only has 1, 2, two significant digits. Here we have 14,900. Now, because these are trailing zeros with no decimal point, but this zero is underlined, now we have 1, 2, 3, and then 4 significant digits. Here we have 47.80. The 4, the 7, and the 8 are all significant because they are all non-zero numbers. And because this 0 appears after the decimal point, then it is as well significant. So right here you have 4 significant digits. And the same rule applies here with 2 zeros after the decimal point. So you have 1, 2, 3, 4 significant digits. Lastly, the 8 and the 9, of course, as they are non-zero numbers, are significant. But these 2 zeros right here are sandwich zeros, and so they also become significant. So now you have 4 significant digits in 80,090, but because this 0 is a trailing 0 with no decimal point, then this number has only 4 significant digits as well. At the end of solving a question, you usually will have to round your answer to a certain number of significant digits. After completing a calculation, you round only your final answer with the following rules. If the end digit is greater than 5, then round up. So for example, 157.8 is rounded up to 158. If the end digit is less than 5, round down. So for example, 34.3 would be rounded down to 34. If your end digit is equal to 5, followed by 0 or nothing at all, round to the nearest even digit. And so 88.5 would be rounded down to 88, while 89.5 would be rounded up to 90. But if your end digit is equal to 5, followed by a non-zero digit at any point, then round up. So for an example, 66.51 is rounded up to 67. And even if you had, for example, 66.5000, how many zeros you want to add, and there's a 1 at the end, this would still be rounded up to 67. Okay, now let's round the following to 4 significant digits. With our first example here, our 4th significant digit is 1. It is followed by a 9, which is greater than 5, and so we are able to round to, let me just draw an arrow, 10.02 because we round up. In the next example, this is our 4th significant digit, but the digit we intend to discard is less than 5, and so we round this to 319,300. And in our final example here, now the 4th significant digit is a 2, and it is followed by a 5. So normally you'd want to round down to 10.22 because that is the nearest even digit, but because there is a 2 following the 5 at some point, which is a non-zero digit, we must instead round up to 10.23. Next, how do you perform arithmetic operations while handling significant digits? When adding or subtracting, round to the fewest number of decimal places. When multiplying or dividing, round to the fewest number of significant digits. And for multi-step operations involving both addition and subtraction and multiplication and division, round to the fewest number of significant digits, adhering to the same rule as if you were to multiply or divide. Now, solve the following expressions to the appropriate number of significant digits. In our first expression, we are adding 12.36 with 4.2, and if you do this in your calculator, you get 16.56. Now, when we are doing addition, we round to the least amount of decimal places according to all the numbers within the expression. In 12.36, there are 2 decimal places, but in 4.2, there's 1 decimal place. And because this is the least amount of decimal places, then we have to round our final answer to 1 decimal place, Because 6 is greater than 5, we round up, and so our final answer for the first expression is 16.6. In the second expression, we are working with multiplication. The product here is 6.72. Now, when working with multiplication and division, as I mentioned earlier, you round to the least amount of significant digits. 3.20 has 1, 2, 3 significant digits, while 2.1 has only 2 significant digits. And so we round our answer to only 2 significant digits, and because 2 is less than 5, we round down. So our final answer is 6.7. Now here we have a multi-step operation, a multi-step expression. First, and as per BEDMAS, we are going to multiply 8.40 by 2.3, and so we have 19.32 plus 1.15. We are not going to round right now. You only round your final answer at the end of the operation, at the end of your calculation. And so we add these two numbers together, and we get 20.47. If we look at how many significant digits each number has, the first number, 8.40, has 3. The second has only 2 significant digits, and the third has 3 significant digits. And so we are only going to be rounding our answer to 2 significant digits. Since 4 is less than 5, we round down. And so our final answer here is going to be 20. Wonderful. Let's go over what we have learned in this lesson. We have learned the difference between analog and digital measuring instruments, how to record measurements involving absolute uncertainty, as well as significant digits, the fundamental rules behind them, how to round with them, and how to perform arithmetic operations involving significant digits. We will build on these ideas in the next lesson by going over types of errors involving systematic and random errors, the concepts of precision and accuracy, and how to quantify errors using the terms percent error and percent difference. Thanks for watching. If this video helped you out, consider leaving a like and subscribe so you can follow along with the rest of my grade 11 physics lessons.